Alright, so this is going to be the solutions to our problems using Coulomb's law with superposition. So here's the first set of problems, the tutorials that we have. We'll start with part A. So we have two positive point charges, Q and Q, which are held in place at a distance s apart. So you've got a little diagram there showing that situation. And the first question they're asking is to indicate the direction of the electric force exerted on each charge by the other. Alright, so I've got this diagram in my sheet here, and we want to indicate the direction of the force. Now, to determine the direction of the force, we have to look at the sign of the charge, right? So we know the phrase opposites attract, so if the opposite charges, one's positive, one's negative, those will be attracted to one another, and if they have the same charge or like charges, whether they're both negative or both positive, then they're going to repel from one another. So we're looking at the situation where we've got two positive charges, and so they should both be repelling from one another. So that means that my force on Q down at the bottom here should be pointing down, and the force from the bottom charge on the top charge will be pointing up. Right, these two charges are repelling one another. Okay, so we've got the direction of the electric force. Second question is looking at the relative magnitude of these two charges. So is the force on little q by the big Q greater than, less than, or equal to this other force? So we want to look at the relative size of these two forces, right? And our options here are going to be greater than, equal to, or less than. Right, now even just looking at the form of these two forces, we should be getting some idea about what the correct answer for this is. And it is going to be that these two forces are equal. All right, so the force from the one charge on the other is equal to the other on the one. All right, and this is because these two forces are forming a Newton's third law pair, right? So they are equal in magnitude and opposite in direction, and we can see that using the subscripts. The other way we can see this is by writing out Coulomb's law in more detail for each of these. So for the left-hand side here, I could have K, Q, Q over S squared, right? So the product of these two charges, the absolute value of them, divided by the distance between them squared. And then I can do this again for the other force. And if I want to be really specific, since I've changed my actor and object, maybe I'll change the order of the charges. Right, but at the end of the day, we should be able to see that this is going to give us the same value. All right, so these two forces are going to be equal to one another. All right, and then 3, or A3, right, by what factor would the magnitude of the electric force on Q, little q, charge change if the charges were instead separated by a distance of 2s? All right, so we're looking at this force and we're saying, well, what's going to happen to the force if we double the distance between them? Now, one thing that we should be able to tell right off of the bat is that if we're increasing the distance between these two forces, then we should be decreasing the overall force, right? This is an inverse square law. So as the distance between two charges increases, then the force should decrease. But we can be a little bit more specific than that. All right, we've got the original force right here, right? So each of these is our original force, and then we want to see what this new force is if I double the distance between them. So I can write that down. All right, so I've just replaced s with 2s. Now the mistake that a lot of people will make is they'll just put a 2 in the denominator, and they'll say, okay, so the force is decreased by a factor of 2, or decreased by 1/2. But in reality, what we're doing in this new case is we're saying r is now equal to 2s rather than r being equal to s in the original situation. So once I put in 2s for r, I have to square that as well. And so that's going to get this factor of 1/4 out in the front. And so I can say that my new force is 1/4 of my original, my OG, I'm actually going to write it OG force, right? Because this quantity here, KQQ over S squared, right, is the same as my original force. All right, so I should get a value that's smaller, 1, and also it should be a fourth the actual size of the original force, whatever that is. Okay, moving on to part B. We have a new situation where we've got 2 or more charges that are held in place the same distance, 2 more charges that are held in place the same s distance away from little q. And so we're going to be looking at these students. So first I'm going to get this diagram into my notes here. All right, so let's look at that conversation and see which student we agree with. All right, so the first student says the net electric force on little q is now 3 times as large as before, since there is now 3 positive charges exerting forces on it. And student 2 says, no, I don't think so. The force from the big Q on the left will cancel the force from the big Q on the right, and the net electric force will be the same as in part A. All right, so both of these students have elements of their answers that are correct, and they both have elements that are incorrect. So the final answer to this should be that we disagree with both students, but let's see why. All right, so we're looking at the net force on small q. So we want to know something about that. So let's start by putting the forces on our diagram for little q. All right, so again, these will be repulsive forces, as we saw in the first problem. All right, so I should have my 3 forces looking something like this. The magnitudes are a little bit off, but we get the general idea about their direction. All right, so the first student said that the net electric force on Q is now 3 times as large as before. All right, so that statement is going to be incorrect, and we can see that because we're looking at these 3 different vector quantities. Right, vector quantities meaning that we've got direction as well as magnitude, and so we have to account for that direction. And so since these 3 vectors are all pointing in different directions, they're not just going to add up to become 3 times as large. All right, so the mistake that that first student is making is he's treating the force like a scalar quantity, where we could just add the 3 forces up without having to think about their direction, rather than a vector quantity where we do in fact have to think about the direction. All right, and then looking at the second student's answer, he's saying the force from the charge on the left will cancel with the force from the charge on the right. So again, this is true and not true at the same time. There is a part of the force that's going to cancel out. Specifically, each of these forces has an x component associated with it. So I'm going to draw those x components into my diagram here. Let's get rid of this s. I think we know the distance. All right, so I'm going to have an x component from the left-hand side here. So this is 3 on q in the x direction, and there's going to be another one for the force from 1 on q, again in the x direction, right? And these 2 forces are going to cancel out with one another. So there is a portion of the force that's being canceled out, just like student 2 said, but there's also going to be a component, specifically 2 y components of each of these forces that will not be canceled out. All right, so these y components might look something like this. And those 2 y components will add to the force from my charge 2 on q, and so we should end up with a force that's larger than the force that we found in part A. All right, so the end result of this is that we're saying that the force is greater. The force in this specific situation in part B will be greater than the forces in part A, but it'll be less than 3 times that force from part A. All right, so we've indicated the direction of the net electric force. If we go back, we can do that a little bit more concisely. This diagram's getting a little bit overwhelmed, so let's start from scratch. All right, so if this is my positive charge, little q, then I can draw the net force on here. Alright, so this will be the net force, and that'll be the sum of those three forces. So F2 on Q plus the Y components of 3 on Q and 1 on Q. Alright, and then what, if anything, can be said about how the magnitude of the net electric force on small q changes when the two big Q charges are added? Alright, so to again summarize what I've said so far, we're saying that the force for part B, this net force for B, is going to be greater than the force from part A, but less than 3 times the force from part A, as that student had indicated, student 1 had said, or more generally, the net force will increase when these two other charges are added. Okay, and last, but certainly not least, we're going to rank these 4 cases according to the magnitude of the net electric force on little q, and as we are making this ranking, we'll be explaining why we're getting there in the first place. Okay, so the first part of this is actually not too bad. One of the things that we can notice is that in case B, I've exchanged Q for 3Q. Alright, and this is going back to student 1's explanation up here where he's saying it's going to be 3 times as large as before. Alright, so this would be creating a force that's 3 times as large as the force in part A. So case B has a force that's 3 times as large as part A. And then case A is identical to what we were doing in part B. Right, and so we already said that the net force in A has to be less than 3 times force in B. So the other way that we can say this is to say in part C, right, we know that case A has to be less than case B. Alright, we know that A has to be less than case B based on what we did in part B. Alright, I can also do a comparison between A and C. Those are very similar, except now instead of this being a circular shape where they're all the same distance, now I've got this straight line between them. And so what that tells me is that the charges big Q's on the left and right hand side in case C are going to be farther away from little q than they are in case A. Alright, now the larger the distance, the smaller the force, and so we're decreasing the magnitude of that force, and so that tells us that the net force in case C has to be less than the net force in case A. Alright, the net force in case C has to be less than the net force in case A. Alright, again, the further the big Q's on the left and right are farther away in case C, and that's going to decrease the force that they can exert on them. Alright, and then last, I'm going to look at situations B and D. This is probably the trickiest comparison. Alright, so we see that we're going to have a force that's going to be pointing up on little q again, just like we did last time, but there's also now going to be a force that's pointing loosely to the right. So the net forces, or the individual forces in this case, are going to look like so. And then what that tells me is that the net force for this charge will be the sum of these two forces. Now, since we're not dealing with actual magnitudes at this point, it's good enough to have just a rough diagram of what this is going to look like. So the net force I can find using the head to tail summation. So I'm going to move my F2 up. Right, the head of F1 is at the tail of F2, and then I can draw my net force in from the tail of F1 to the head of F2. All right, head to tail summation. Size is actually going to be roughly the same as the hypotenuse between this right triangle, so from here to here. And so what that tells us is that this F net in this case will be greater than F1 or F2 individually. All right, the magnitude of that force will have to be larger than either of them alone. So if the magnitude of the net force in case D is larger than either of the component forces, and one of those component forces is the force from case B, and so that F1 is the same size as the net force in case B, that tells us that the force in case D has to be greater than B. So case B is less than D. All right, and last we can actually just put these three inequalities together. All right, so if D is greater than B and B is greater than A, then we know that D is greater than B, which is greater than A, and we know that A is greater than C, and so C has to be the smallest. All right, so C is the smallest, then A, then B, then D. All right, so C is the smallest. Right, with this extra distance between them, then A, where they move in a little bit closer, then B, right, where I've got the full three vectors rather than just the components of them in either cases A or C, and then again case D being the hardest to place, but will be a larger force than in case B alone because of that extra force that's being added from the negative 3q. Okay. All right, here's the last problem that we had to look at the net electric force. We want to practice looking at the force from Coulomb's law, or the electric force in 2 dimensions, and so that's what this problem is doing. So let's start with a free body diagram, just like we have for each of these problems. Alright, so our free body diagram has 2 forces on it. One is the attractive force from the charge down by our right angle here, our negative charge, and then a repulsive force from our other 1 microcoulomb charge on the other vertice. I will note that I've informally given these charges designations of 1, 2, and 3, and we can see that over in my knowns. Right, so this is charge 1, 2, and 3, just to help us keep track. And then I've also denoted the distances using that subscript as well. So R12 is the 8 centimeter distance between charges 1 and 2. R13 is the 10 centimeter distance between charges 1 and 3. All right. So we've got this force that's at an angle, force 3-1, which is going to be at an angle, and we need to know something about that angle in order to find the net force in the x direction and then the net force in the y direction, so that we can ultimately get to the net electric force, right? So F net 1, as well as the direction, where that direction should be an angle, or will be an angle in this case, rather than simply positive or negative in a certain direction, because it's going to be in both the x and the y directions. All right, so what I'm going to do is I'm going to solve for this angle theta right here in my triangle. I'm picking that angle because if I add my force onto my diagram, then I should be able to see that theta will also be right here. So theta will also be right here, and I can use that to resolve the individual components of my force. Alright, so to find that angle, I'm going to use my inverse trig functions. I'm given the adjacent side, my 8 centimeters, and the hypotenuse, 10 centimeters, so that's going to be cosine. So I can use the inverse cosine and do R1, 2 over R1, 3 in order to get that angle. So 8 over 10 in the inverse cosine. I believe it's something like 36 degrees. Alright, so that angle is going to help me get the individual components of this force. So my x component of my force I can find with the magnitude times the sine of theta, right? The x component is going to be the sine of theta, and then the y component will be a positive magnitude times the cosine of theta to get my y component. Alright, so then the net force in the x direction is equal to the sum of the forces in the x direction. And in this case, there's just the one. And I can write this out a little bit more formally. And then I can also find the net force in the y direction. So the net force in the y direction is equal to the sum of the forces. That's a sketchy sigma. Sum of the forces in the y direction. So I've got the y component of the force from 3 on 1, and that's going to be positive. So I'll have a positive force of 3 on 1 times the cosine of theta, right, to get that y component, and then that will be reduced by the magnitude of the force from 2 on 1, right, which is pointing down, so it'll be subtracting. Right, again, I can write this out a little bit more expansively. Alright, and I can get values for each of these. Normally, I would not recommend doing any calculations until we get to the very end, but I'm going to make an exception in this case, just so we can see what direction this net force is going to be pointing. Alright, so when I did the calculations for this, I got the net force in the x direction as something like negative 0.43152 newtons, and in the y direction a negative 0.09889 newtons. Right, so the main thing that I'm interested in right now is the fact that both of these answers are negative. Alright, so this means that my net force is going to end up being in my third quadrant, and so I can add that into my diagram. And so it's going to look something like this. Alright, but we still need to find the actual magnitude and direction. Right now I've got the components of my vector, but that's not what I'm being asked to find. Alright, so to go from the components to a magnitude and direction, right, on this net force vector, which we're saying is in the third quadrant. Alright, so to find the magnitude of this vector, I can just use the Pythagorean theorem. And then to find the angle, which I've called phi, right, usually the direction we find relative to the x-axis, I can use inverse tangent. And those will give me my final answers. All right, I've got a final answer for the net force, a magnitude, so that's always positive, of 0.442706, and an angle of 12.9074, and that is below the negative x-axis. Newtons. Should consider sig figs at some point, not that way, this way, and this way. Here we go. Okay, 2, 2, 2, 2, 2. All right, so 2 sig fig problem. So final answer is going to be 0.44 newtons and 13 degrees below the negative x-axis.